Welcome back to Part 9. In our last section, we stepped away from the software interface to build a firm conceptual foundation around how basic events behave quantitatively. We established that the entire quantitative analysis relies on breaking our safety elements down into two major categories: demand-based failures and time-based failures. As we saw in our theoretical slides, the demand-based category is reserved for event-driven risks, where we look at a static probability of failure at the exact moment a system trigger occurs. Within the time-based framework, we introduced the two most commonly used models in reliability engineering: the constant failure and repair rate model and the dormant model. These three explicit modeling types, demand-based probability, constant rates, and dormant standby, are the exact vehicles we will use to define every single root cause in our reactor vessel case study. Now that we are back inside the item toolkit interface, I want to introduce a highly powerful efficiency feature called the failure model library. Instead of forcing you to manually type in the exact same failure parameters over and over again for every single basic event, the toolkit contains a built-in library facility designed to store, manage, and retrieve commonly used mathematical models. It also allows you to build custom templates from scratch. You can access this facility by going to the Edit menu and selecting Failure Model Library. The failure models defined here are shared between all systems, including fault tree, reliability block diagram, or event tree systems. Using the library provides a massive technical advantage beyond just saving you repetitive data entry, because it creates a centralized master template. Whenever you change a parameter within a library model, every single basic event across your entire fault tree that references that model will update automatically. This global synchronization ensures absolute consistency and eliminates the risk of human error when updating failure rates or testing frequencies across large-scale models. When you open up the Failure Model Library dialog window, it is organized into a clean layout to help keep your project templates tidy. On the left side of your window, you'll see a tree structure. This is a three-level hierarchy. The top level, or root node, is labeled Failure Models and shows an integer count of how many failure models are currently sitting inside your project library. The second level lists each stored failure model by its unique name, and the third level explicitly displays any basic events in your tree that are dependent on or currently linked to that specific model template. Whenever you click on a model name at the second level, it instantly updates the Preview tab on the right side of the screen with its corresponding parameters. To begin building our project library, let's select the Failure Models root node on the left hierarchy and click the New Model button located at the bottom of the dialog window. We will now systematically define the parameters for each component category. 1. External Power Grid, Grid. For our first model, let's change the name to Grid. Set the model type to Rate Model from the drop-down menu. In the parameter fields, enter 1.0 for the failure rate and 1000 for the repair rate. 2. Electronic Isolation Valves, EV. Click New Model again. Name this model EV. Set the type to Dormant. For the parameters, enter a failure rate of 0.7, an MTTR of 0.006, and an inspection interval of 0.1. 3. Manual Isolation Valves, MV. Click New Model to add the next line and name it MV. Keep the type as Dormant. Input a failure rate of 1.0, an MTTR of 0.001, and set the inspection interval to 0.5. 4. Electronic Controller Subsystems, CON. Click New Model and name it CON. Set the type to Dormant. Enter 0.05 as the failure rate, 0.002 as the MTTR, and an inspection interval of 1. 5. Temperature Sensors, TS. Click New Model and enter the name TS. Select Dormant as the type. Populate the fields with a failure rate of 0.05, an MTTR of 0.001, and an inspection interval of 1. 6. Pressure Sensors, PS. Click New Model and name it PS. With the type set to Dormant, type in 0.2 for the failure rate, 0.001 for the MTTR, and 1 for the inspection interval. 7. Emergency Alarms, Alarm. Click New Model and name this template Alarm. Set the type to Dormant. Input a failure rate of 0.2, an MTTR of 0.004, and an inspection interval of 1. 8. Non-return relief valves, NRV. Click New Model and name it NRV. Select Dormant as the type. Enter a failure rate of 0.05, an MTTR of 0.001, and an inspection interval of 0.1. 9. Human Operator Response, OP. Finally, let's click New Model one last time for our human element. Name this model OP. Because this is a static, demand-based event rather than a time-dependent one, select Fixed as the model type and type in 0.01 in the unavailability field. Now that all 9 failure models are fully defined, you can see them neatly organized under our library tree hierarchy. We are officially ready to begin linking these master templates to the basic events on our fault tree canvas. Now that our library is populated, we need to link these master templates to the actual basic events in our project. There are 2 different ways to accomplish this in the item toolkit, and I will demonstrate both. Method 1. Graphical canvas assignment. The first approach is to interact directly with the fault tree diagram. For instance, if we locate our non-return valve event, NRV, on the canvas and double-click it, the Event Parameters dialog pops up. By navigating to the Failure Model tab, we can click the drop-down menu and select the NRV template we just created. As you can see on screen, as soon as it is selected, all the failure rates and inspection intervals we defined in our library are automatically loaded right into the dialog. Method 2. Centralized Event List Assignment. While double-clicking works perfectly for a quick adjustment, going through a massive diagram event by event can become incredibly tedious. Fortunately, the toolkit provides a powerful, centralized alternative. If we close this window and go to the top menu, select Edit, and click Event List, it will open up the Global Fault Tree Event List dialog. Let's select the Show All Event option at the top to populate the grid below with every single event currently resting in our tree. From this single spreadsheet view, we can click on any event in the list and click the Event Parameter button to open the exact same assignment window. Since we have already linked our NRV event using the diagram canvas, let's use this centralized window to efficiently map the rest of our tree one by one. First, select the Alarm event, open its parameters, and choose the Alarm Failure Model. Select CON and choose the CON Failure Model for our electronic controller. Select EV1 and assign the EV Failure Model. Select EV2 and assign that same EV Failure Model template. Select MV1 and choose the MV Failure Model for our first manual valve line. Select MV2 and assign it to the MV Failure Model as well. Select the Human Error event, OP, and link it to our fixed OP Failure Model. Select PS1 and choose the PS Failure Model for our pressure sensor. Finally, select TS1 and choose our TS Temperature Sensor Failure Model. With all of our basic events successfully tied back to their centralized master templates, our fault tree structure is completely quantified and mathematically locked in. Let's click OK to close the grid, save our project locally, and prepare to execute our primary system calculations. Now, looking closely at our event list, you will notice that the grid event is completely missing from the current fault tree structure. This is entirely intentional. Keeping the grid unlinked at this stage allows us to study different operational scenarios where the power grid is used to energize different parts of the system, giving us a clean way to analyze how changing our electrical configurations directly impacts the overall system risk profile. With all of our on-canvas basic events successfully tied back to their centralized master templates, our primary fault tree structure is completely quantified. Let's click OK to close the grid, save our project, and prepare for our next section where we will put these scenarios to the test. To summarize what we've accomplished in this section, we transitioned back into the Item Toolkit interface and successfully transformed our qualitative logic structure into a fully functional, quantitative safety model. We leveraged the centralized failure model library to build 9 distinct master templates, defining our rate model parameters, dormant model testing frequencies, and fixed event-driven probabilities. We then explored how to efficiently bind these templates across our entire project, both graphically from the canvas and in batch using the Global Event List Manager. Finally, We left our grid model intentionally unlinked so we can cleanly simulate different power configuration scenarios. Now that our parameters are locked in and our data is structurally complete, we are ready to let the software run its calculations. In our next section, we will step back and thoroughly discuss all of the quantitative results we retrieve from the fault tree we've created. We will look at system unavailability, cut sets, and importance measures, and most importantly, we'll cover exactly how to interpret these metrics to make informed engineering risk decisions. Thank you for watching, and I will see you in the next section.